and audio, video, and so on. And there's one that is labeled probably sharing slides or something.
Yeah, ask to share slides.
It says share preloaded slides.
Share right. So I need to just share preloaded slides, and then you get a list, and then you select your presentation, and then you have the control and can move forward and so on.
But wait till we're done our chair's introduction, and it's 7:30, so we can get started anytime.
Okay.
Right. But if there are any issues, let us know, and we can also just run them for you. Okay. Yeah. Welcome everybody to Icnrg at IETF 113 in Vienna. Yeah, special greetings to our friends in the room. Thanks, Matthias, for being our on-site co-chair today. It doesn't look like we will have lots of questions from the room today, but let's see. So Matthias is going to manage that in case there's something to be done. Hello, Thomas. I see you in the back. Okay. Yeah, I'm the co-chair. My co-chair is Dave Horan, and so I think you probably have seen this slide now on day 5 of the meeting, but yeah, so just make sure that you are using the Meet Echo Lite tool if you are in the room, and if you're not talking or presenting, turn off your mic and video as always. Of course, this session is recorded. Just quickly, we still apply the IETF IPR rules, so let us know. So in summary, let us know if there's anything IPR related that you see being discussed here. Right, so everything is recorded. The IETF is using the IETF privacy and code of conduct rules, and we also have anti-harassment procedures. So if in case of any issue, we have an ombuds team that you can contact. And quick reminder, so we are doing research here and not standards development. The best we can do is like publishing experimental specifications as RFCs. So the idea is in general to enable research and generate insights for the IETF or the general internet community. Okay, today we are supported again by Marie-José. Thank you very, very much. Really appreciate. So Marie-José is taking the notes in the Headstock note-taking system. I pasted the link into the chat. If you want to follow along or assist in the note-taking, you are welcome to do so. And this is our agenda. So we have a really nice agenda today. So yeah, I'm not going to read this, just asking, is there anything else that you want to add or you want to say about the agenda? Okay, great. So before we get to Edmund's presentation, let's just quickly check where we are in the group. So we recently had a really nice flow of outputs from Icnrg, so RFCs being published, and we have a few more that we want to get out. So CCN Info is, I think, still waiting, yeah, for IRSG reviews. We're going to talk about Flick later. ICN LTE basically went through the ISG conflict review, and the authors just published a new version. And as far as I understand, what Colin is asking for right now is a statement on the IPR situation. So would be great if the authors could really clarify that as soon as possible to get this published soon. And I see Colin joining the queue.
Yeah, just quickly on
Yeah.
that one. The issue there is that there was an IPR declaration on the individual draft before it was adopted as a research group draft, which hasn't been right for the research group draft. So we're just waiting on clarification on whether that's still relevant or if the draft has changed such that it isn't. But other than
Is it just me, or is your audio breaking up?
Same here.
it's possibly
Seems to be on your side, Colin.
here. Is that better?
Yeah, I think so.
Yeah. My laptop runs out of CPU with all the video streams, and it makes the audio. All I was saying there was that the IPR issue is that there was an IPR declaration on the individual draft before it was adopted by the research group draft, which hasn't then been reflected onto the research group draft. So we're just looking for clarification on whether that still applies, and if so, it needs to be updated for the research group draft.
Yeah. Okay. Thanks. Dirk Trossen is at the microphone.
Yeah. Hi. As I mentioned to Colin, because he's been polling the authors, while I have no IPR declaration, obviously the draft was initiated when I was with my previous company. The problem is, as you may recognize, given the current situation, I can't query with the company directly. They won't reply to any email that I send directly. So we need to figure out how to get in touch with InterDigital to figure out if there's any IPR that may be pending. I can't declare. I mean, from my side, I say no, but I don't feel comfortable in doing that 100%. So Colin, maybe I can give you a couple of names and you may ping them. They may reply to you. If I do that, they won't.
I can, if you think it's necessary. That they've already made an IPR declaration for that draft. So.
Oh, okay, good. Oh, I didn't realize that. Good, thank you.
It's really just clarifying. Okay, yeah, thanks for that. And then you may have noticed that there have been new versions of ICN ping and ICN traceroute recently. So we want to publish these specifications soon as well. And so right now they're waiting for the shepherd. Oops, and that's me. So I'll take care of this very soon. And Dave, do you know the status of the NRS architecture considerations draft? We can't hear you. At least I can't hear you.
Yeah, same here. You're muted.
So I think this is actually done. So we're waiting for it to be published. So maybe Dave can come back later and clarify any questions that may arise. Okay. So with that, let's move to our first presentation. And Colin.
Is my audio working?
Yep.
So for the NRS Arch considerations, I think it's with the RFC editor, isn't it?
Yeah, right. So that's what it said. I think it's done. So there's nothing we can do at the moment. All right. Okay. So Edmund, are you ready?
Yes. So I've requested to share slides, right? So here we go.
And
so I do, okay.
I think it's coming up.
And then I should share, right? Okay,
yeah. Looking good.
Then I can just operate it from here, right?
Yeah, you can use your cursor keys and so
Okay.
on.
All right, great. Thank you, Dirk, and thank you, Dave, for inviting me to present today for the Icnrg meeting. So I'm Edmund Ye from Northeastern University, and this talk is about a project that we have been pursuing for the past more than a year. It's called NDN for Data Intensive Science Experiments, NDs for short. Um, so this is actually a follow-on to a project which is called Sandy, which started in 2017, and I believe 2 years ago I made a presentation to Icnrg about Sandy and NDs, and of course at that time it was more preliminary. So the project concerns data-intensive science. So the examples that we're considering here are examples such as Large Hadron Collider, high energy physics, LSST, the Largest Synoptic Survey Telescope, or SKA, or genomics. These types of science applications, essentially you have a situation where there is an enormous amount of data being taken either at one or a number of different locations around the world. In the case of Large Hadron Collider, of course, the data is being taken in CERN and in Geneva, and that information then has to be distributed around the world to a couple of hundred different institutions for analysis. And these are very big data volumes that have to be distributed, and they are distributed for analysis purposes and computation purposes. And so we had started this collaboration almost 5 years back, and there exists actually a problem in this area because the data volumes here, for instance, for Large Hadron Collider, are set to grow very fast, almost 10 times due to high luminosity, what are so-called high luminosity experiments coming up. They're already on it's in the order of exabytes, and is set to grow another 10 times in the next couple of years. And even given the considerable resources that LHC network has, they're still going to have a lot of problems in handling this data volume and distribute it around the world. So they actually sought out NDN, and particularly our group, to work with them to build a new system for them as a future system that can distribute this data more effectively for the LHC community. So this particular project is funded under the CC STAR program by the NSF, and the team consists of myself, who's I'm the lead for the project at Caltech. Our co-PI is Harvey Newman, who is someone who has been involved with the LHC High Energy Physics Network for many, many years. We also have from UCLA, Lisha Zhang and Jason Kong. So Lisha, of course, has been a leader of the NDN team for a long time, and Jason Kong is an expert in FPGAs from UCLA. We also have participation from Susmit Shanagrahi from Tennessee Tech, and Susmit has been working with NDN team for a long time also, and he had previously worked in the climate area using NDN for climate. And of course, we're in partnership with LHC, the genomics collaborators, and the NDN project team at large. We're also interested in this particular project on genomic data, although that work is still more preliminary compared to the work for high energy physics. There is a need to use diverse computation, storage, and networking resources to meet the challenges that have been posed by these data-intensive science fields. And I think during my last talk 2 years ago, I outlined the need to essentially build a system with an architecture which is more appropriate for the needs of these applications, which are very much data centered around data. So the traditional architectures, which centers on connections and servers and processes, are not especially well suited for these applications, whereas we believe that NDN is well suited. And what we're doing is to build a data-centric ecosystem for providing agile, integrated, interoperable solutions for heterogeneous data-intensive domains. That is sort of the overall goal. And INDES is an important project in furthering this goal. I want to make sure that yes. So what are the goals of NDES in particular? It is to deploy and commission the first prototype production-ready NDN-based petascale data distribution, caching, access computation system serving major science programs. So it actually has an ambitious goal of really putting in a system that can work for data-intensive science based on NDN. LHC high-energy physics is the leading target use case. Biogenome, human genome projects, Atlas, LSST, SKA are future use cases. We want to leverage NDN protocols, high throughput forwarding caching methods, containerization techniques, integrated with SDN methods and FPGA acceleration subsystems to deliver LHC data over wide area networks at throughputs approaching 100 gigabits per second. So we want to really build a system that delivers data over a real wide area network. And a lot of the work actually is in interfacing with entities such as Internet2, ESNet, to actually put this network together and test it over the geographical, it's basically cross-country right now in the United States. We would like to dramatically decrease download times by using optimized caching. We're building an enhanced WAN testbed with high-performance NDN data cache servers. All right, so this talk is really about updating the progress of NDES, what have we done over the last year or so. So I would like to talk about a few things that this team has been doing. I would like to discuss the NDES deployment architecture and NDN-C, which is an integration of NDN CXX with NDN DPDK for the purposes of the NDES project. I'd like to discuss the WAN testbed and the throughput tests that we've been performing, and also the experiments that we've been doing with optimized caching and forwarding. I'd like to discuss the congestion control work that is currently ongoing in the UCLA group, and how that's interfacing with caching considerations, and also discuss the FPGA acceleration work that Professor Kong's group has been doing at UCLA. All right, so let's first talk about the deployment architecture in NDN-C. So here's basically the deployment architecture, and to me this looks a little bit small actually. I hope you guys can all see it, see it full screen here. You can see that we have basically on the left here, you can look at it as the consumer side, and on the right hand side is the producer side. We have developed a containerized setup where you see that we're building Docker containers, which enables us to make this work for various kinds of operating systems. And these CMSSW jobs are jobs which are generated for within the LHC system. So these are jobs which require that would require certain calls to certain data sets. And Icnrg the Icnrg plugin is essentially a plugin that interfaces with the between the calls within the LHC networking environment, and then turns these requests into essentially NDN consumers. And from there, we have a set of functions which are implemented using extensions of NDN CXX and interfacing with NDN DPDK, the NDN DPDK forwarder, through something called MMIF. And we then go through a network, which is a high-speed network having capacity up to 100 gigabits per second. In the right-hand side, you see essentially the producer side and operating, finally interfacing with a number of different services being provided by the LHC system. So I hope we can see that, but let me describe this a little bit in detail. So the Caltech group has built something called NDNC, which is a lightweight integration of NDN CXX with NDN DPDK to achieve high throughput performance in scientific applications. So you can see the code there in that link. It uses the MMIF shared memory packet interface to provide high performance packet transmit and receive functions between user application and the vector packet processing within NDN DPDK. So I'm going to skip some of the details here. Each phase can transmit and receive one or many of these blocks in a single burst, and it offers PIT token support, which is something that is needed by NDN DPDK. And it uses this NDN CXX library to encode and decode layer 2, layer 3 packets. It also has support for congestion window and retransmission, either fixed or AIMD. This is something that we're still playing around with a little bit to see how these congestion windows should be set. But this is built in the NDNC system. Future plans for NDNC: we'd like to do extensive benchmarking to understand the current behavior and maximum throughput performance that can be achieved, identify possible bottlenecks, add multi-threaded support to MMIF and pipelines. Currently, that's single-threaded, as we mentioned over here. And we would like to port the NDN Icnrg plugin developed in our previous project to NDNC. And we want to extend the number of applications to cover some of these services that are provided by the LHC network and the file systems they have. Okay, so let me talk about the WAN testbed and the throughput test that we've been doing. So, okay, here's the testbed that we've put together, and in fact, putting together this testbed has actually been a major time sink for us. But it's worthwhile because this is the high performance testbed that we wanted to have. So it has a number of nodes here. Basically, it involves the participant institutions of So Northeastern, the node is actually sitting in MGH PCC, which is a shared computing facility between MIT, Harvard, Northeastern, and BU. There's a node at UCLA. There's a node at Tennessee Tech. There's multiple machines at Caltech, and we are also very happy to have the collaboration of Starlight in Chicago. So you see, this is a topology. Essentially, it's a fully connected network here, and with different link capacities here. We have very high capacity, high speed links of 100 gigabits per second between Northeastern all the way to Caltech, and then some of the links are smaller capacities, 10 gigabits per second. But these are, it's a pretty high performance network and running across the country here. And you also see the specifications, the configurations for the machines sitting on this network. So we have quite a bit of flexibility.
Edmund,
Yes.
do you allow questions in between, or should we do them at the end?
I'm open. So
Okay.
yes.
Ken, go ahead.
Hi, Edmund.
Hi, Ken.
Are these running? Are these all over Internet 2? And is it L2 stitching?
Yes,
is that what they are? Okay.
Yeah,
Thank you.
we put this together with a lot of collaboration from Internet 2, ESNet, yeah, this is running at layer 2. Yeah, so we have these VLANs. The numbers you see there are VLAN numbers which have been provisioned, and in fact, just doing the provisioning, the VLANs sometimes can take months to accomplish, as you know, if you work on these things. But yeah, it took quite a bit of time for us to put this thing together, but it is operating.
These are dedicated. There's a dedicated host at each one of these sites. Is that right?
Yes.
Or are they?
Yes.
Are they?
Well, some of those machines are shared, but so the machines that sitting at the participant institutions, they're all dedicated. The machine at Starlight, I think is shared, but it's not heavily used by other applications. Yeah.
Okay. Thanks.
Mm-hmm. Yeah. So this is the network that we're currently experimenting over, and it's an incredible actually resource that we actually have here, because we're able to do real experiments on a wide area network basis. It also, of course, requires a lot of upkeep. For the throughput test, I won't go through all the details here, but basically, we actually wanted to do the throughput test from on the 100 gigabit link from Northeastern to Caltech, but because of various reasons, the VLAN from Starlight to Caltech was only recently put up. So we ended up doing the throughput test basically on that orange link here that you see. But basically what that does is it sets up a loop at Starlight between two machines sitting at Starlight. The path actually goes from Starlight in Chicago to Canada and then back to Starlight. So but we do have a consumer and producer on two different machines, and the capacity of that link, that path, is basically 40 gigabits per second according to iPerf. And you can see the configurations of the machines there. We have 2 threads for each consumer application, and running 3 forwarding threads, launching 6 consumers simultaneously. Currently, we're using a fixed window size for congestion, and there are various reasons for that. Well, we have a dedicated path there, basically. And we're sending the files, which are 1 gigabyte to each. These are evenly allocated on the 3 forwarding threads, and we are caching these files at the producer so they can access them quickly, and we request them from the consumer machine. So what we're getting here, and we're really trying to push the throughput on this path here, is for, you can see that over a span of 6 minutes, we averaged throughput over the different consumers is listed for the total of about 21 gigabits per second. That's the highest numbers that we got. We're still playing around with the different configurations in this setup, but this is currently the throughput numbers that we've been getting on. This is all over a wide area network. This is a real WAN network over continental distances. And so far, I think that's the highest number that we have gotten over the past few years. We previously had gotten some numbers more in, I think at SC19 we had 6.7 gigabits per second, and at SC21 we achieve about 14. So, you know, we are definitely pushing that throughput and understanding better what kind of what the system is capable of. Of course, this is, you know, running the consumer producer that we have written, and working with, integrated with NDN DPDK, and you can show that really NDN is capable of high performance over real wide area networks. Okay, now let me talk about caching and forwarding. And so this is also a big part of the project, is that to try to test in a real experimental setting these caching algorithms that were first developed by my group at Northeastern. So we're using this test bed in two different, here I'm showing two different sets of results. One where we have two consumers at UCLA and Starlight, and going through a forwarder at Northeastern, and then ending with a producer at Caltech. And another one with two forwarders in the middle, one at Northeastern and one at Tennessee Tech. And we have 30 files, which each file is 4 gigabytes, and we generate requests at the consumers according to a ZIF distribution. And we run this caching algorithm, which has been developed by my group called VIP. And we will then compare the performance of that to a case where you do not cache anything, or you use kind of LRU kind of caching, or an improved version of that, which is actually within the NDN DPDK implementation called ARC. So these are real experimental results. Here, what I'm plotting is the different colors corresponding to the different file indices. So file 1 is the most popular one according to the ZIF distribution. File 30 is the least popular one. And they're ordered like this. And now the algorithm that we're running, the caching algorithm we're running, it doesn't know the ZIF distribution beforehand. It actually just adaptively measures these things and adapts the caching pattern adaptively in real time without any prior knowledge. And so here what we're plotting is basically the cache score, which is output by the which is put out by the VIP algorithm. And you can see that actually at the forwarder node where the cache is, the cache score of that most popular file is actually the highest. You can see that they're ordered in the right way. And if you actually see what is actually cached at the forwarder node, you see that it's caching exactly what it's supposed to cache. So the cache is capable of caching 5 files, and it caches 1, 2, 3, 4, 5. So this is exactly what it caches after, you know, some stabilization. We run it for a few minutes, and now what's interesting here is we plot the result of compare the performance of the different scenarios here. On the x-axis is the throughput in gigabits per second. On the y-axis is the delay. Okay, that's actually the download delay. So you see that the numbers for, so we plotted the numbers for what you get at Starlight, what you get at UCLA, and the overall average. And the square ones are one for VIP. The circles are for the ARC, which is a version of LRU, and the triangles are for the case where you use no cache. So you can see that VIP is actually getting lower delay and also more throughput in general. The differences between ARC here is not big, but in the next experiment, you will see that that actually gets bigger. So you see that the effect of caching is basically to increase throughput at the same time as decreasing delay, because essentially because you bring it closer to the consumer and you decrease delay that way, but also because you make unnecessary further transmissions of the request upstream. Therefore, you sort of reduce congestion in the network and you further reduce delay, and you also increase throughput. So you have both the effects here. Now, in the next,
And then just a real quick question: is this DRAM caching, or do you actually have external I/O going on?
yeah, this is using caching in the yeah. Let me. So this is caching using no, this is DRAM caching. Yeah. Mm-hmm.
Great, thanks.
Yep. Right. So the next experiment. Let me see. Oh, here. Yeah. Yeah. So in test 2, remember in test 2 we have two nodes, right? 2 nodes in this, so 2 caching sites, and in this case, at the first one, you see that at the northeastern one. So what you expect here, I would just want to point this out. In the second one, where you have the 2 nodes here, you would expect that the first caching point should cache the top 5 most popular files, and then the next 5 should be cached over here, right? That's what you would expect. In fact, that is pretty much what happens. So you can see at the first forwarder, you cache the top 5. Okay, in the next forwarder, you essentially cache the next 5, but with some minor variations here. Now this I think has to do with essentially the stochastic variations of the algorithm, but overall you see that it is the files that are being the right files are being cached here, and of course the algorithm is doing this completely adaptively. It doesn't know this beforehand. So the result here for test 2, you can see again, VIP is doing essentially the best everywhere, as it did in the previous case. But in this case, the improvement is even more pronounced. It has greater throughput and lower delay than compared with ARC, and certainly compared with no caching. So this shows very clearly that if you are clever about caching, and by the way, we have actually not even totally exploited the full power of VIP, because VIP is actually a joint caching and forwarding algorithm. So because here in a topology, we really don't have much in the way of multipath capability. So we're really only leveraging the power of caching, and already we're getting a lot of improvement in the performance. So the next step for us is really to test out these topologies over the WAN that has more multipath capability, and I think we'll get even better results. But it takes time to do that, and we'll report that in the future. All right, so let me see what I can say. I don't know how much time we still have, but I want to say briefly about what the work that has been happening in congestion control and FPGA acceleration. So Lisha's group at UCLA has been working on congestion control, and they've actually been working on the impact of caching on congestion control. So there are some interesting examples they've been studying. So for instance, in this particular example, you have 2 consumers, C1, C2, that are fetching the same object from the producer P, and the objects are segmented. However, C1 has a higher capacity, higher speed connection to F1, which is a caching point, and C2 has a slower connection. So the expectation is that C1, the C2 is going to start first. Okay, C2 is going to start first, And the expectation is that C1 will initially be satisfied by the cache because C2 pulls the object first and caches it at F1. So C1 will initially be satisfied by the cache and later catch up with C2 and eventually be satisfied by the producer. However, what is actually observed, so you see that C1, because it has a higher bandwidth, your expectation is that it would first get it from the cache and then later catch up with C2 and be satisfied by the producer, right? But what actually happens in simulation is that C1 may never catch up with C2 or be satisfied by the producer. Instead, it will continue to be satisfied by the cache, and C2 will be soliciting data in steady state. And the reason is that so here's a plot of what you expect to happen in terms of this is the x-axis is a time and y-axis is the delay that is observed by C1. So you would expect that it first gets it from the cache to F1 and then gradually would take over and then eventually would get it from the producer. But because what happens is that so the scheme that I think Lisha is working on is, the congestion the control is based on looking at the difference between the interest sending rate and the data receiving rate, so that C1 will essentially look at this and interpret this difference because it's getting it from the receiving rate is essentially lower than the sending rate. So it interprets this as a congestion signal and actually decreases its request rate. So what happens is it actually then never catches up with C2. The observation here is that this is some somewhat unexpected way in which the congestion control interacts with the caching, so that they're still exploring this, and they're interested in working out congestion control measurements which must be resilient to these RTT variations. So what they have done so far is they have developed a multi-path interest forwarding, they've developed a hop-by-hop congestion control design that uses queuing delay as a control signal, and it's hop by hop. It's still, I don't think it's published, but this is well under development, and this is able to respond to different kinds of bandwidth limitations upstream, and it uses the queuing delay as a signal, which is propagated hop by hop to from downstream to control the sending rate, the request rate. Of course, then the question is, how does this interact with caching? And that's the question that they're exploring right now. And we'll report on more details on this later. All right, so let me say something about FPGA acceleration. So this is the group of Jason Kong working on the FPGA acceleration. FPGAs are used in a wide variety of applications in machine learning, in networking, in IP longest prefix matching, packet inspection for firewalls, and so forth. Why use FPGAs? They are capable of pipelining tasks. Each cycle can start up a new IP lookup, for instance. It can do parallel processing. Multiple interfaces of its own have its own processing block instead of sharing one. So there are many benefits. The goal is the goal is to use FPGA in the forwarder input stage. So we're talking about the Indian DPDK forwarder, where the components of the interest name have to be hashed, and there has to be a table lookup to see which interest packet should be dispatched to which forwarding thread. And so there essentially you have to do the prefix hashing, and you have to do the table lookup, and those are both computationally expensive, and this is what the FPGA will be designed to do. And we're still in the preliminary stages of this, but there has been some progress. So again, looking at the hashing of prefixes and name components, table lookup for thread dispatching, preliminary results show a 4-time improvement over doing this all in the CPU. 4 times improvement in terms of the throughput. But the integration with ND and DPDK is still ongoing. So there's actually multiple stages to this. First, we will apply the FPGA acceleration to the NDT, which is the dispatch table for the input in the ND and DPDK forwarder. Then we will apply it in a similar way to the combined PIT CS table, and finally to the FIB. So we are still in the first stage, but there's some promising results of having some throughput improvement. Okay, so I think I've run over time. So to give you some summary, I mean, of course, it's really a progress report, what I have said here, just to give you some results, and we're still working hard on that. But I think we've achieved quite a bit. I mean, just having the WAN testbed put together was actually a major achievement as far as we're concerned. We have a high-performance ND's deployment architecture with containerization and integration with ND and DPDK using NDNC. We've established a high-performance ND's WAN testbed. We have managed to obtain a throughput of roughly 21 gigabits per second over this testbed. And we've shown that optimized caching forwarding yields significant improvements in both delay and throughput over this testbed. These are real experiments. We have been developing hop-by-hop congestion control based on queuing delay, looking at interactions with caching, FPGA acceleration of hashing of name prefixes, and table lookup for thread dispatching shows a 4 times improvement over CPU. We're doing this in CPU. And we're working toward the prototype production-ready NDN system. And we are seeking on the long-term collaboration with other domain sciences, networking, computer systems communities. All right, thank you very much.
Great. Thanks a lot, Edmund, for this really interesting presentation. Let's see whether there are some questions.
Mm-hmm.
So one question that I had was, so I mean, this is obviously, a lot of work went into setting up this testbed and really accelerating this data access for these large data sets and so on. I was wondering, so once you are able to do that, often you want to do something with the data. So it's like processing the data. Is that also in scope of the NDIS project?
Yeah, it's a good question. So it was actually in the proposal, there was a section in the original proposal, it was proposed that we would also look at joint data movement and computation scheduling of these workflows. But due to then the budget was cut a little bit, so we removed that from the scope of the project for now. Obviously, that's the ultimate goal of hopefully a continuation of this project, is to not only deal with the data movement, which is what we're doing right now, but to handle the workflows. And that's something that's definitely very, very relevant. And this is the whole problem in high energy physics application and many of these other applications. So I think there's still a lot of work that remains to be done. But I think that the data movement is definitely the first step.
Okay, yeah, cool.
Mm-hmm.
So we have Thomas in the queue.
Hello, Edmund. Thanks for this very interesting talk. A question on your caching analysis. I mean, you're considering high energy physics or other huge bulk scientific data, and you were assuming a zip distribution. I was a bit surprised about this. I mean, I would expect zip with Netflix, but is there a use pattern that actually distinguishes between certain portions of the data in high energy physics?
So we actually took statistics using actual request data from the LHC community. And in fact, there is a similar fall off, that you would expect in, I mean, usually you have data sets which are so-called hot data sets, which everybody wants to work on, so there is actually a fall off in the popularity, and we fit actually the distribution with the ZIF one. It's a good approximation. So this is actually based on data that we collected. Is that your question, or is it?
Yes, it does. Thanks.
Yeah. So it's a similar phenomena actually is true in physics, because what happens is that there's typically some big questions that everybody is trying to explore, right? And that requires certain data sets, which are maybe the most recent one, or some data set which is really relevant to the task at hand. And then there's of course a tail and falls off. Yeah.
Okay, next question from Ken.
Thanks, Edmund. You may, as you may know, we're trying to do some similar. We're trying to build on some of your Sandy stuff, actually, and you've probably seen from my master's student. But my question is, when you in the 3-hop thing where you showed the architecture of the consumer and the producer, what did you develop a bespoke transport protocol for that, or are you using some kind of generic chunking protocol to break up these very large data sets into segments? And is it designed for this application, or is it just a generic chunking protocol?
So the question is, how do we chunk? Yeah, I'm trying to find this. So I think it's okay. So I think these are. So I'm not sure if my student is online right now, but maybe he can give you better details on this. I'm not sure. I think he's there.
Feel free to. You can answer offline if that's easier. It's just
okay.
Yeah.
So I think that chunking is essentially is something that is essentially inherent in the application. So I don't know if Yuanhao, are you able to speak quickly or no? I guess he has to ask to speak or something, right?
He can just unmute himself.
Okay, Yuanhao? Yes.
Yeah.
Something about chunking.
Yeah, the chunking is implemented directly embedded into the file server and the consumer application. How to chunk the content, and so the file server is basically where do all the things for us to chunk content.
But that's something that was developed by NDNC, right?
NDNC and the NDN-DPDK group, the NIST group, they developed file server.
Yeah. Okay, that's what I wanted to know, is whether it's part of DBDK or NDNC or something like that, or is it actually built into the application? But yeah, I'll just send you an email and ask you that question.
Yeah, let's talk about it more. Yeah. So thanks, Yuanhao. Thanks, Ken.
Okay. One more question, and that's the final one by Dave.
Well, I'm going to abuse my queue location and ask 2 questions. Hopefully, they're both real easy ones. Number 1, at your 21 gigabits per second, are you doing signature validation?
I do not believe so. Yuanhao? We're not doing signature validation, right?
Right.
So you're not actually exploiting the security properties of NDN.
Yeah. So what happens is this in the I mean, that's a good question. In the high energy physics application, I mean, that's something we will be doing. I think that's the sort of the provenance aspect is a part of the project, but right now we're not doing that. And in fact, the physics application, what happens is that you have a sort of a pretty strict security parameter for people who can access the system. You have to be approved and so on and so forth. So they don't actually usually worry about security too much within the physics application. But nevertheless, as a part of the project, we did propose to put the signature, to sign the packets and to verify them, to provide provenance. So we haven't done that yet.
Okay, and then one final quick question, which is 4x improvement over CPU for an FPGA seems not very impressive. Do you have any insight into what the bottleneck is?
Yeah. Yeah, you're right. I think it's not. I think that these results are still preliminary, to tell the truth. I think Jason's group is still working on that.
Well, just for the future, I'm really interested in this subject. Dirk and I have been working on some stuff that's going to be bottlenecked on FPGA style hashing of these load distribution to cores. So I think that works of really broad interest, and publishing some stuff on that would be really great.
Well,
Thanks.
So I absolutely. I don't want to say anything definitive here because Jason's group is really the expert on that. We can take this offline, and I can probably give you more insight talking with their group about, but it's ongoing work. You shouldn't see this as finalized by any means.
Trying to do network coding the same way was that if you can't exploit the high parallelism by doing 20, 50, 70 packets at a time in the FPGA, you're just not, because the inherent clock rate of the FPGA isn't just all that high, right?
Mm-hmm.
So you really need to be able to parallelize things.
Absolutely. So I think you're right. I think this is not that impressive yet. But the FPGA work, I have to say, it is ramping up. The first part of the project was much more focused on these other things that I talked about, the caching and setting up the WAN testbed. But I think during the next couple of months, we should be seeing much more ramping up of the work on FPGA, and we'll keep you updated.
Great, thanks.
Okay, thanks. So I'm sure people have more questions, so have I, but yeah, let's defer this to the mail list. I'm sure Edmund will be happy to answer your questions. Thanks again, Edmund, for being
Very
here
much.
at this early time.
Yeah, thanks for the opportunity.
Hope to see you again soon.
Yeah, of course. Thank you.
Okay, so let's move on. And next would be Cheng Gunuwan on data time encoding for CCNX.
Yes, thanks, Dirk. Hi, Dirk. Hi, Dave. Hi, Vienna. I think you can hear me right.
Yeah,
the audio is
very well.
I'm asking to share slides.
Yes, granted.
So I can see my slides now.
Looking good.
All right. Yeah, thanks again for this 5-minute slot that you provided us. So this draft is about a compact time representation for CCNX. It was actually first presented in 2019, I think in Singapore by Thomas Schmidt, and then in 2020 virtually by me. So far, it hasn't received that much attention on the mailing list, and that's why I wanted to also give like a brief recap on the core ideas of this draft. So in resource-constrained environments, we have usually like a low bandwidth and a high latency. Access to wireless links is typically slower than the packet processing within the stack itself. And the packet transmission is usually the dominating factor for like the energy consumption of these little tiny devices. And header compression is actually a solution to reduce the energy expenditure, but it also improves transmission reliability, which we also measured and showed during our work on ICN Open, which is now RFC 9139. So CCNX is making use of two different types of representing time. First, they have relative time, which is used in the interest for the interest lifetime. And there's also absolute time, which is used for the signature time, expiry time, and the recommended cache time in both message types. The relative time is unbounded. This means that the TLV supports an unlimited number of bytes that you can use to represent the offset. And the absolute time is limited to 8 bytes to encode the Unix time in milliseconds. And in this particular draft, we are the idea got inspired by RFC 5497, which is time TLV RFC it's a time present or like a dynamic range encoding for Manet routing style protocols. And this is all very similar to the work in IEEE 754, which is the floating point standard. And the idea is that we encode the exponent and the mantissa of a number into a single byte. And using the formulas that you can see at the bottom of the slides, we can calculate a time value, which is in seconds then, from this one single byte. The subnormal form of this formula is needed to solve actually the underflow issue, because if you only go with the normalized formula, then you have a huge jump between 0 and the smallest number you can represent. So in the last presentation in 2020, we actually presented like multiple configurations for this single byte, because you can play around with the mantissa and the exponent sizes and come to like different ranges. And so also on the mailing list, we had this discussion 2 years back, and I think this is the configuration that we converged to, and this is also now in the draft. And with this configuration, we can have numbers that range from 0. You can see on the left side of the table, there's the subnormal range, and then it goes in 7 millisecond increments until the normal range and normalized range, and from there on it goes logarithmically until a very huge number, which in this case represents close to 4 years.
And Cenk, can we ask some questions? And,
yeah, sure.
So Ken is in the queue.
Sorry, I just forgot to leave the queue. I don't have a question right now.
Okay. Then Dave is in the queue.
Yes, Dave.
I forgot to remove myself.
Oh, okay. I'm sorry. And then okay. Sorry, Cenk. Please go ahead.
All right. So if there are any questions, then please raise the hand. So from here on, there was this huge question also 2 years back on how actually we can integrate this compact time in the current CCNX protocol specification. And there were like multiple solutions to that. The solution that Mark Moscow was also giving a lot of input on the mailing list for that. So the solution we went with currently in the draft is that if we, for example, look at the interest lifetime, we say that if we set the length to 1, then the forwarder has to interpret this number as like the compact delta time. And if it's like any number greater 1, then it's the typical CCNX time delta in milliseconds. For the recommended cache time, it's a little bit different. I said before it's fixed to 8. So it's not actually using other sizes. there. So what we said in the draft is, okay, if we use a length of 1, then we put the compact time in there, but you probably saw it's a delta time, so it's a time offset and not an absolute time anymore. But we think that the recommended cache time is not so critical if you lose a little bit of precision there. So the forwarder must be able to convert the time offset to an absolute time on return, on transmission and receiving the packets. So there's obviously, well, the advantage of this integration level is that we don't need to allocate a new TLV number at the IANA. But the disadvantage is that this requires an update to the CCNX messages RFC, and that if there's a forwarder that doesn't know about this change, then of course the time is like misinterpreted. I think that was also one of the core arguments for Hitoshi. I can see that Hitoshi, sorry, I can see that he's in the chat at least. So maybe he has something to say to that. So an alternative integration would be to actually define a new top-level TLV. So to allocate a number at IANA, and then we would have something like interest lifetime compact, and this would live like next to the typical interest lifetime. Of course, the advantage is that if a forwarder doesn't know this, the TLV probably just ignores it and takes a default interest lifetime. Yeah, the disadvantage is we allocate that number. And this brings us to the end. So there's, yeah, within the 2 years, there were like very subtle changes to the draft itself. The div to version 3 was actually just to describe the integration level that I just showed you in the last slide. And the div to version 4 is that we changed the formula to streamline it more to what time TLV was saying, and what we chose for ICNOPAN. And there's a pseudocode in the draft that specifies how to encode the actual numbers, and we had to update this according to the formulas, and also we added terminology and acknowledgement sections. Yeah, you probably saw we need more feedback also on the mailing list, especially for the protocol integration. So how to integrate these compact times into CCNX. And also there's the expiry and signature time, which is currently absolute time. And there were some ideas floating around a couple of years back, whether we can generate time offsets for these TLVs. The problem is that they are within the security envelope, so it's not that easy to change that on the forwarding. But maybe we can also find a solution for them. So, and then the question, I mean, if there's interest in the group for this particular work, then would this be ready for RG adoption?
All right. Thanks, Cenk, for progressing this and for bringing this back. Yeah, so I mean, we think this is the right type of document for a research group activity. It's kind of it's a useful feature, especially in these high delay environments, and it's raising interesting questions on protocol extensibility. So like from a chair's perspective, I think we would propose adopting this. We will reconfirm this on the mailing list, but in general, I think this is the right type of document for that. Is there any immediate feedback on Cenk's questions, so the protocol integration or the encoding? Okay, because that's what we need, of course, as a next step. So to then make a decision in the group how we want to go about integrating this, especially. And yeah, so let's discuss this on the list then.
All right.
Thanks again, Cenk.
Yep, thanks.
All right. So we're moving on with the updates on ping and trace route. So Spiros can't make it today, so Dave is going to present these things.
So hi, Spiros couldn't make it. He did the slides, so I'm just going to quickly go through things. on ping and trace route. So just to remind people, these are instrumentation and management tools for NDN and CCN style ICN protocols, and they're analogous to the similar capabilities we have in ping and trace route in the IP world, although because the architecture of the underlying protocols is different, the capabilities of these protocols are similarly somewhat different in terms of how they support multipath and how they can support the existence of caching in intermediate nodes. So ping gives you the reachability of names both from producers and on-path caches. And we have, again, packet formats for both of our popular NDN underlying protocols. Ditto for traceroute. This is a multipath capable traceroute, just as we've seen in the IP world with tunnel trace types of things, but this is now built in on day one. And similarly, we have protocol encodings for both our popular ICN protocols. So the current status is that these drafts have been around for quite a while. They've been implemented in a number of experimental settings. We completed last call in January. Didn't get a lot of feedback, but we got some very good set of comments from Junxiao Shi on the draft, and both have been since updated by the authors. So we had one issue that came up on last call, which had to do with just how to integrate path steering, which is used in the multipath case for both ping and trace route, into the encoding methodology of this, and decided, based on some discussion, that it belongs in the base protocol as opposed to some intermediate link mapping protocol, because although it's not an end-to-end capability, it is modified hop by hop, but the actual process on each hop is independent of the link type. So the changes in the current version, very quickly, very few. Packet format was updated for the latest version of the NDN formats. We moved the TLV that carries path steering outside after the signature TLV to make sure that it's excluded from the security envelope, since it is modified hop by hop, and made use of the new capabilities in NDN to have types name components. NDN didn't have that until fairly recently. So we use type name components both in the CCNX and the NDN variants of the protocols to indicate that ping and trace route require special processing by intermediate nodes. So the next steps is basically the authors think the drafts are ready for IRSG review, and Dirk has is going to have to be the documents that shepherd, since your other co-chair is a co-author of the draft. And I'm done, and I'll take questions. Okay, I think we're done. Yes?
Yeah, I'll take care of it. If there are no questions, let's move on with the path steering.
Oh, one quick thing just for Colin. I'll confirm this with the mail to you, but these two documents are essentially a pair. So the same IRSG person that will probably want to review both, since they're just two peas in a pod.
Colin said, makes sense.
Okay, I guess I'm up for the next one as well. Dirk, you want to introduce it?
Yes, so the next one is a refresher on also work that has been done earlier, and that's path steering. So yeah, an interesting capability that we can introduce to ICN, so make path selection available to consumers. And we think it's quite relevant for like the multipath discussions that keep coming up, and like also deficiencies that other protocols have in this direction. And so that's why we thought it's a good idea to look at this again and make people aware. So yeah, Dave, go ahead.
Is everybody else seeing the messed up conversion slide on this stuff?
Yes.
On the title slide?
Oh, that's not on purpose. Okay.
So, well, we do have a capability of encrypting the path labels. So maybe that's just the encrypted version. It's supposed to say path steering or refresher. All right. So this has been around for a while. And we haven't had a lot of strong motivation to move it forward quickly until recently. And the reason the motivation's gone up, of course, is because we're progressing ping and traceroute, both of which need this in order to be maximally useful as instrumentation tools in a multipath forwarding environment. Because you want to be able to make sure that when you're measuring, for example, RTTs, that when there's a multipath environment, you get individual RTTs for each of the subpaths that might be traversed. And similarly for traceroute, you want to be able to explore for multiple paths to destinations and be able to report on them. So I'll quickly go through this. A lot of this is material you may have seen before, but we haven't really talked about it in a while. So it's probably worth taking a little bit of time to go through it again. So, the underlying problem statement is that ICN communication is inherently multipath and multi-destination. So we don't today have a mechanism for consumers to direct traffic, interest traffic onto specific paths. We do have forwarding strategies in ICN that could spray interests onto various paths, but consumers have a hard time interpreting whether there are any failures or performance glitches when multiple paths are being used. So we need the ability for troubleshooting and performance tools to get this path visibility in order to find problems and do simple measurements. And we discovered the same thing in the IP world when we tried to do things like MPLS and tunnel trace, where there are multiple underlying paths. And hence a lot of work was done sort of like late in the evolution of the IP protocol suite to add these capabilities. And as a result, it was quite substantially messy. So we're hoping that by incorporating these capabilities early in the evolution of the ICN architectures, that we'll be able to do a much cleaner job. So what we'd like to be able to do is discover and monitor and troubleshoot a multipath network connectivity environment, and accurately be able to measure the performance of a specific network path when there are multiple paths. Similarly, we have a number of already published and implemented multipath congestion control algorithms, some of which, not all of which, but some of which work by estimating and counting the number of available paths, identifying paths, and actually allocating traffic to each path explicitly. So we have two that have been published over the last couple of years, one called MERC, multipath rate-based congestion control algorithm, and SMIC, a subpath window-based multipath congestion control algorithm, both of which would be able to properly exploit an explicit path steering capability. So the design of this actually goes back to a paper published around 2018 on path steering and also path switching, which does optimized forwarding paths using path steering. So the design question is, how do you label the paths? And over the last few years, we've looked at a number of possibilities. You can use Bloom filters, which are probabilistically pretty good. We looked at what are called pairing functions, which have minimal overhead in terms of storage, but require some multi-dimensional math in order to compute them, and don't deal with long paths very well. We looked at label stacks similar to MPLS label stacking, which has some nice history behind it. And they're known to work reasonably well, but require being able to vary the size of the data structure as you traverse the network with the push and pop operations. We chose to use fixed size labels simply because we expect path length to be not unreasonably long, and the processing of these to be really, really fast. So the second issue is, how do you discover paths, and how do you steer packets on the paths that are discovered? So one of the nice properties that makes this way easier than in the IP world is that we have symmetric forwarding, symmetric routing, so that packets returning are returning over the same path that the interest is forwarded over. So the interest contains a path label marked in discovery. It's forwarded via the least name prefix match in the fib, and the content in a data message carries the path label that's been computed on the way up back towards the source of the packet. And then a subsequent interest can take this path label that was obtained from an earlier return data packet, not marked discovery mode, and forwarded via the fib and this explicit next hop selection. So we don't bypass fib lookup here. We simply use the path label to select the particular outgoing face among the possible faces that are already in the fib. I say that because the original paper also had this optimization of being able to elide the path, the actual fib lookup. So we can reliably measure path RTTs. We can iteratively discover multiple network paths. Congestion control can discover and distribute load across paths. And although this hasn't been proven in anything implemented yet, if you believe you might be getting a content poisoning attack across one of these paths, and you have multiple paths that could bypass a poison cache, consumers potentially can mitigate the effect of a content poisoning attack. And we can also potentially build traffic engineering solutions if path labels can be distributed via SDN style route distribution. So some of the interesting issues are how you deal with route updates. So you have to be able to invalidate paths that have been discovered. So we have an interest return in CCNX style NAC for carrying an invalid path label, which can invalidate it. You could silently forward the interest through any available next hop if you don't get a match. And we can actually control this behavior by either forcing the error or allowing you to fall back or redo discovery. The next obvious problem is how you deal with route updates. We assign new next hop labels every time the fib changes, and on the reverse path, we drop the data or the NAC so that you can invalidate the path. So the last piece of this, which is the only piece that's really changed recently, is how we do the packet encoding. So on CCNX, we add a new error code so that you can report broken path labels. There's a next hop header that carries the path label, and the sub TLVs that go with that in order to complete the encoding. On NDN, NDN hasn't adopted this, but we have a proposal in the spec for how we believe should integrate this into the NDN packet encoding, which is to have a new packet TLV called path label with essentially the same semantics as we've defined for CCNX. There's just a picture of what it looks like. Now, there's some security considerations here. They're all in the document. You can look at them. Clearly, consumers could do probing and maliciously missteer packets. But in order to be able to guess a correct next hop on a different path, you have to sort of send about 2 to the 12th interests for this to work. So we have a number of mitigations, in the spec in order to deal with that. And I just unshared my slides. Let me put them back up again. Just a second. Oop. There we go. Back to security considerations. So a second possibility is cache pollution by consumers and producers colluding to inject off-path and bogus objects. So cache entries have to be annotated once you add this capability with the corresponding path label, and only use that cache entry to satisfy interests with a matching path label. And that cache entries should not evict entries for the same object with no path label or a different path label to mitigate this potential cache pollution attack. And I'm done. So I think the issue at hand, which we'll talk about when we're done the rest of the agenda, is whether perhaps we should do an RG adoption call for this work at this point. So thanks very much.
Thanks, Dave.
Ken.
Sorry, forgot to raise that. Okay, I'm going to say the words you should never say at a IETF meeting, but I have a question, but I haven't read the draft, at least not recently. So what is it that could you put the picture of the encoding up again, because I didn't quite digest that. Okay, so it's a 12-bit next hop label, and the idea is that it's completely up to the next hop what to put in there. It can be a random token.
Correct.
Okay.
Correct.
That's
it just gets recorded in the fib as an identifier for that face in that fib entry.
Okay, and there's a link. And I mean, it could be at the AS level, or it could be at the node level, or whatever, right? Or are you even?
The intent is that since you want to be able to use this for diagnostic purposes as much as possible, the intent is that it would be every hop would be identified.
Okay, thank you.
Oh, and please read the draft. We're interested in your comments.
I will.
Other questions? Yeah, so I mean, we think this is quite a powerful tool that gives consumers many ways to influence the way they want to work with the network, and it's designed in a way that is using soft state and so on. So it's something that other protocols cannot really do, and so that's why I think it's a really nice also illustration of how ICN could work or could be leveraged.
Yeah, I mean, this is way less messy than doing similar things in the IP world because of the symmetric routing properties of our ICN protocols.
Right. Okay, shall we move on? Okay, so I'm going to the next one. So one of the reasons we put up path steering on the agenda was actually that, so when Dave and I were discussing how to redesign reflexive forwarding, path steering was one of the candidates, but in the end we decided not to use it So this is about reflexive forwarding for CCNX and NDN. And so let me just talk a bit about the motivation. So I mean, there are many demonstrated scenarios where, you know, ICN interest data is just fine, very useful. So like Edmunds, you know, data science environments, but also IoT and multimedia streaming and so on. But there are also other scenarios where it's not quite sufficient. So when you would think about how would we, for example, do web over ICN, so something like RESTful communication. So I'm going to explain why that's a problem, or things like remote method invocation, or like maybe phoning home scenarios in the IoT world, or peer state synchronization. So often in this scenario, you need something like the ability to push data to somewhere, and or you want to have like a sequence of say interactions with like RESTful semantics, and so you need to establish some state and pass some parameters for every request and so on. And so these are, of course, relevant use cases. And so, I mean, in the past, research has tried to somehow, you know, realize them sometimes with, say, maybe, if I can say so, maybe like some hacky approaches. And so the goal for our work here was to enable these scenarios in a way that doesn't completely contradict, say, all the ICN paradigms that we you know, enjoy so much. So having no source addresses, flow balance, and so on. So we think that the scheme here could be a foundation for these scenarios and possibly others as well. And so RESTful ICN, I think that's something that would be needed in, say, anything that has to do with web in the future, for example. So what's the problem for these kinds of interactions? So take web, for example. When you do RESTful communication, you set up a connection to some server. You often transfer many input parameters, authentication, authorization, some kind of tokens, and so on. And quite often you do this with every request, so something like cookies and so on. And so if you look into how like web requests look like today, so the header fields and sometimes also the size of the body is really quite large, and so you wouldn't put this into an interest if you can avoid it. So that wouldn't really make sense. And another example is remote method invocation. So for distributed computing, another use case where ICN gets more relevant. So you actually think about how would I include my authentication information? How would I include like potentially large data sets that are needed for some kind of computation on the server side and so on. And then, yeah, so the way that you would typically do this is enable some multi-way handshakes. So, for example, for RMI, you would maybe like want to fetch the arguments somehow if you want to do it in an ICN compatible way, and maybe then perform some authorization. And then other scenarios where you could utilize multi-way handshakes when you do IoT and you have like phone home scenarios. So sometimes you like have something to tell to your home base, but yeah, you don't want like the say cloud-based server to poll you all the time, but you want to notify the server, and then you want the server to fetch the data from you. So there you would utilize multi-way handshakes. Or for any type of peer state synchronization where you need at least 3 handshakes to do this reliably. And so the question is, okay, how would we deal with all these scenarios in ICN? And okay, we have seen some, say, proposals where people just stuff in additional parameters into interest messages. Why is this not a good idea? Well, when we want to like employ congestion control based on say, the data object size and rate, it's could be detrimental to just send uncontrolled interest with very huge message sizes. Also, well, if you think about this RMI scenario, so like client-server communication, if you just push a lot of data to the server that the server needs to analyze to make a decision whether this is a valid request or not, well, this opens the door for, say, well-known computational overload attacks. And you wouldn't want to do this. You want to give the server, say, more control in what he wants to accept and what not. Also, of course, if you think about pending interests on forwarders, that would mean extra state. And if interests are too big that they get fragmented, that's also highly undesirable. And okay, you could say if you want to do multi-handshakes, okay, let's just include some kind of ICN name into the interest that the producer can then use to query additional data. So the issue with that is, so suddenly you would require consumers to reveal something like a source address or a source name, which, well, normally we wouldn't have to do in ICN. And I think it's quite a desirable feature for many reasons. So you could say maybe pseudo anonymity, but also consumer mobility becomes more difficult, right? When you don't have source addresses, it's very easy to move the consumer. But like having a routable address or name that the server needs to know makes this way harder. And so it also would probably result in quite complicated state machines if you have to deal with like multiple exchanges in parallel and so on. And so with reflexive forwarding, we tried to overcome these issues and basically make it possible for a producer or say server to ask for additional data that it needs to perform some transaction perhaps. But we don't want to do it in a way that suddenly the server has to know some kind of routable prefix or like stable name for the consumer. And so what we want to do is basically allow the server to send what we call reflexive interest back to the consumer, leveraging the state in the forwarding system that an initial interest created. So you send an interest to a server, somehow this allows the server to implicitly get back to you, but it doesn't need to have a routable and stable source address for the consumer. And also we want to couple the state that is needed for these, say, interim interest data exchanges in the opposite direction to the overall state of the, say, general interest data exchange. And yeah, this is how maybe it's better to explain it with a picture. This is how you could explain the general operation. So a consumer would send an initial interest, and so this has the usual ICN name to identify the, say, named object on a server, but has additional information. So a reflexive name prefix that we then use to get back to the consumer. So let's just assume that this interest arrives at the producer, and so it enables the producer to maybe check some initial parameters and then decide whether it wants to continue with this interaction and then fetch additional data. And so this could be several interactions, not only one. And then make maybe stepwise decisions how to move on, what else is needed, and so on. So RNP is this reflexive name prefix that we want to communicate. And then, so once the, say, reflexive data has arrived, this would enable the producer to kind of do the computation or complete the transaction and then return a regular data object, D1 here in the end. And I see Thomas in the queue. Yeah, please go ahead.
So if I look, if I look at this picture, then I would expect that any consumer is able to send to a single producer such a request with a reflexive name prefix, which means looks to me like a very nice DOS attack vector, isn't it? So if you have a botnet, you send from many places, you send this RNP X1, and X1 is actually your victim, and then you're pretty well in the game.
That's something that you have to avoid, of course. So maybe let me continue with the explanation, and then I think it becomes clear. So in the previous version that we talked about some meetings back, the system worked in a way that we actually expected forwarders to install a FIP entry in a, say, separate database that would then later allow them to forward these reflexive interest back to the consumer. And so this kind of works. You can do it this way. And so it's the say forwarding information here is still bound to this say outer interest data exchange. And so when, for example, the D1 data object gets sent back, then the forwarders would also remove this reflexive FIP information. But of course, it has the disadvantage that you have to maintain this extra data structure and manipulate the forward information base and so on. And so we thought about, okay, how could we maybe make this a bit more elegant, a bit more, it's maybe easier to implement as well. And so the current version was actually inspired by the PIT token approach that the high-speed NDN DPDK forwarder used. So this was published in a paper at ICN 2020. And this is a system that Edmund talked about earlier. So in these high-speed forwarders, you have additional interesting challenges. So you often have sharded PITs because you have multi-core forwarding, and you want to give the forwarders an efficient way to map and an incoming data object to the to the correct picked instance in a sharded system. And so we thought, okay, PIT tokens, so which has been used for that, is probably a useful feature anyway. So for high-speed forwarding, it's needed for these multi-core sharded PIT systems. And let's leverage that. And so what we have done here is, so we defined like two tokens. So one in the forward direction that we say use in the initial interest, we call forward direction PIT token, FPT. And then another one for the reverse direction that is then kind of leveraging this PIT state that gets established in the forwarding direction first. So maybe let's look at the picture as well. So here we have the consumer sending the I1 interest, so with a regular prefix and also with a reflexive name prefix. So that's a prefix that the consumer chooses. And so with like significant uniqueness, and so when a forwarder gets a interest with a reflexive name prefix, it's supposed to create this forward PIT token and install PIT state for that. So we have our regular PIT entry, maybe with an additional attribute, additional field. I mean, there are different ways to really implement this. And so this contains the information about the reflexive name prefix. And then when we get the I2 interest later, we can then use the same token ID to locate the PIT entry and then make a decision where to forward the interest to. So that means the producer is receiving these interests, is then kind of mirroring this forward PIT token into this reverse PIT token field, and then sends the reflexive interest back to the original consumer. And then the forwarders would be able to use this PIT lookup and make the decision where to forward the interest to. Thomas.
This looks to me as if you assume that the forwarders on your reflexive way back, so this is with interest 2, are actually have seen interest 1.
Absolutely.
But this
absolutely
isn't obvious to me, because I mean, if you forward from the producer interest 1 using the prefix x1, then you're using the FIPS in between, and the FIPS are forward directing, and they need not be the same. I mean, they need not be the mirror of the other FIPS on the way to the producer. So it need not be symmetric, but that's what I'm saying.
Right.
Use fib on the reflexive interest going back.
Sorry?
Say again, Dave.
That's why we don't use the fib on the reflexive interest going back. We map directly onto the PIT entry of the original interest.
Okay.
So and then use the incoming face to forward the reflexive interest.
Yeah. So this absolutely relies on symmetric forwarding. And if you don't have it, then this wouldn't work. Ken.
But now you are using the PIT to forward interests. Is that right? It's the same PIT, or it's not a separate, or it's a different. I'm trying to understand the exact difference between this and what you had before in Rice.
Right. So previously, we actually had to install, say, routing information in the forwarders. And here, I mean, there are different ways to implement it, but here basically the forwarders would see that there is this RPT field, and then this would enable them to look up the token in their PIT.
Okay, so there's a different processing path. When an interest arrives, it has one of these forwarding path tokens.
Right.
Tokens.
So of course, this would also require a modified forwarder behavior, but we think these changes are more benign than manipulating the routing state and maintaining separate tables for that.
Right. I guess I'm just reacting to calling it a PIT entry, because it's really forwarding an interest. It's not a pending. In some sense, it is a pending interest, but is it? I mean, you see this as the same data structure. Is that right?
Well, so this I2 interest here that goes back to the consumer. I mean, first of all, it's a regular interest, except that the name that we are asking for, is this reflexive name prefix that we received in the initial I1 interest. And so it's like mechanically it's a regular interest. It just has an additional field, RPT field, and so this enables the forwarder to determine, okay, where do I have to send this to? But we don't need to disclose any say globally routable name or anything. So this is just the RNP is just a label essentially that the consumer generates.
Thanks.
Right. So these PID tokens are typically hop-by-hop extensions or hop-by-hop features in NDN or the CCNX. So one question is, okay, how do these names actually look like? So I didn't really explain it well, but so the idea is that you would communicate a prefix, and so under this prefix, the consumer could like provide different, or like a set of information, like a cookie, username, or something. It would be different data objects. The draft also explains a bit more about this, like you could use manifests if you have like larger data sets and so on. But the prefix itself, well, it would be a new name component in CCNX and NDN, and it's essentially just a random 128-bit number. So we were referring the UUID, RSCs, how to generate it. And so it's nothing that has any significance outside of this interaction. And this is also why, to Thomas's earlier questions, this wouldn't enable you to do any kind of reflection attacks to non-related or third-party entities in the network. And yeah, so again, so you could use this as a prefix and then construct like different types of names, or maybe just a manifest that then refers to additional objects and so on. So this could also be used for like several interactions. If you think about, say, something like web interaction where you have multiple maybe parameters that are needed for the server to process your request. And yeah, so as we mentioned, so there is, of course, new node behavior required. So details are in the draft for consumers, producers, and forwarders. And but so we haven't really implemented it yet, but we think that the forwarder modifications well, are actually not as invasive as we had it for the previous version. So you need this PID token generation when you receive this interest as the first forwarder on the pass, and when you see an interest with this reflexive name prefix. And so we think this is maybe a good approach if you want to cater for both like high performance forwarders and just standard software based ones. So it's relatively easy to implement, but it still wouldn't screw up performance in these high performance scenarios. Yeah, I'm not sure we have to go through these specifications. So what we provided encodings for both CCNX and NDN, so it's slightly different because they use different mechanisms. Maybe let's talk a bit about what this could enable. So we talked about remote invocation, RESTful, and data pull from sensors. And for RMI, we had this previous work that we called RISE, remote method invocation for ICN. And so there we would also use this system, because we would also have to send some request parameters when we want to initiate a remote method invocation. And just quickly, the way that it would be used there would be that you send your initial interest with the reflective name prefix, and then the server kind of fetches the input arguments, say one by one. And so in this system, then we would have an say additional interaction. We would kind of return the data object here with a handle that allows you to fetch the computation result later. So because well, this should support long-lasting computations and so on. And this is a typical example how we think this would be used. So often you have additional things that you need to communicate. So this restricted and forwarding scheme could just be one element in, say, a more evolved communication pattern. I have to wrap up quickly. I talked about RESTful already. And just quickly for this, say, it's IoT phoning home scenario. So assume you have some asynchronously generated data and you want to get it somewhere. So you could, say, use the I1 interest to kind of notify your data sync or database or whatever, and then this would trigger this reflexive interest and then fetch the actual data item. Okay, let's maybe jump over this. You can, so this security was kind of one of the concerns here. There's some extended discussion in the draft. And what I think we want to convey is that while we think this could be, say, a key element for making ICN fit for future web kind of systems, what is also related here is key exchange when you want to have something like encrypted communication, name privacy, and these things. You also have to convey parameters. And you also have to convey something like a cookie that kind of maybe links to your session and so on. So that's a scheme that we think would be useful in, say, many scenarios, that you would maybe use this forwarding scheme to establish some state later, and then when you have something like a session continuation, you could use a cookie in the interest, in the, say, what we call I1 interest, to just refer to that previous state. And so different protocols need this, or different say, interaction styles need this. So web, key exchange, or say secure communication, and so on. So that's something that could be like a general feature that we want to specify maybe as the next step. Okay, let me wrap this up. We have time for one question. Yeah, Christian.
Hello, Christian Amsus. You mentioned the problem of client or consumer mobility in the context of previous work. Do you have any plans of addressing this here? Because as I understand, this now also doesn't work with the mobile client, but maybe a client could kind of, in later interests, send information that would allow the producer to use the same prefix, different prefixes with the same suffixes, like establishing something like a namespace.
Yeah, so you're right. I mean, say if we have a moving consumer, so within this whole interaction, that would also be a problem, of course. So what we would you could say here is that so between reflexive, say, forwarding interactions, you could still have the usual mobility because you wouldn't disclose any stable name, and so the prefix, the reflexive prefix would be generated by the consumer for every interaction, and so so it's not as bad as using these stable or globally routable names. Thanks for the question. Okay. We'd be really interested to get more feedback. Please give it to us on the mailing list. And let me bring up our share slides again. So Dave, do you want to talk to this? I can't hear you.
Okay, got my audio on. So just a couple things to wrap up. We're just about out of time, but I just want to sort of give people a feel for what's happening in the next period before we get all together again. So we did some progress on Flick a few months ago, and it stalled again. We really would like, a lot of things are depending on having a manifest capability in the architecture. So I guess we're just sort of asking, hey, is there anybody out there who can potentially help us here to try and unstick Flick and get it to RG last call? There's still technical work to be done. It isn't just, you know, dotting I's and crossing T's here. So that's number one issue.
Quick question by Ken on Flick, I think.
Yeah, Ken.
Yeah, it's not a question. I'm just saying I'm in the process of going through it again. It's much improved, but I want to be able to give substantive comments. So I will do that. I will bump that up in priority and try to get something to the list soon.
That would be great. Thank you. We're going to take ping and trace route to IRSG review since last call successfully closed, and we have an updated spec. Dirk is going to do an RG last adoption call on path steering, and please give your feedback on the mailing list as to whether this is appropriate. And then two quick things. Our sort of new work coming in is at a level lower than we would like. Our engagement has obviously been hurt by all the COVID situation and a variety of things, but we are not running out of capacity to deal with interesting new research work that people would like to bring to the group for discussion and potentially work among the participants in Icnrg. So please think about bringing your work in. We may have some interesting possibilities for doing joint work with the computing and the network group, since ICN protocols do actually do a lot of computing in intermediaries because of the complexities of forwarding, and potentially some of the work we're doing on distributed computing fits in ICN as well as with that. And a general question is, we will plan to meet at IETF 114 in Philadelphia in July, but if we have enough stuff going on, we're interested in your views as to whether we should have another interim meeting between now and late July. So that's it. I'm done. I think Dirk and I both thank everybody for your time. We hope to have this face-to-face in Philly. And please remember, we have an annual ICN conference coming up in September. Paper registration deadline is a couple months away, so you still have time to work on your papers. It's our premier research venue for work in the area. So keeping that vibrant and interesting is, of course, interesting to this whole community. So thanks.
Thanks, everybody.
Thank you.
And yeah, see you on the mailing list, hopefully. Check out the discussion on low latency video distribution. I think it's quite interesting what's going on there at the moment.
Great. Thanks again, everybody.
Bye-bye. And a special thanks to our on-site chair, Matthias, and our note taker, Marie-José.
Bye-bye.
Bye.
Yeah.